Okay, now we're going to talk about conservative vector fields. As I have mentioned before, when you want to compute the work from done on a particle by taking it from one point to another, the trajectory that you choose matters for determining that work. And so it is an interesting question if the work is ever independent of the trajectory you choose. Okay, and the answer, or rather a definition, is that we'll say that a vector field is conservative if precisely that happens. So let me just write it like this. So imagine that you want to take a particle from point P to point Q, and I'm saying that you could have chosen different curves In fact, the curves can do many weird things. They could do something like crazy. And so you say, so here's the definition, F, so it's a property about the vector field. F is called conservative vector field if for any points P and Q so the main property of a conservative vector field is that for any points P and Q, the work done on the particle, or the work done, let's just write it this way. Is independent of the trajectory that connects P with Q. Or let's say curve from P to Q. So what I'm saying is that there are many different trajectories you can choose from P to Q. Choose your favorite one, and the work along this one will be the same as the work along this one, which is the same as the work along that one, So conservative vector fields have the feature that the work is path independent. And so question 2 is, are there any conservative vector fields, right? It's not clear. the answer is yes. Probably you know some from physics classes, like for example, the gravitational force is a conservative vector field. So really, the remaining part of the course is to a large extent understand how to figure out if some vector field is conservative or not. So the main goal from now on is to pin down this notion of being conservative. But there's like an easy case where, and like there are different ways to think about a conservative vector field that I'll mention as we move along in different videos. But for now, let's just create this very concretely and say that a vector field, so among all possible vector fields, we'll say that a vector field emits a potential. Okay, so let's talk about potential functions. So a vector field F emits a scalar potential V, well, or emits a scalar potential if you can find a scalar field or a scalar function B such that F is the gradient of that function. So in physics you would typically write this with a negative sign. I'll maybe mention later why that's the case. But for now, what I'm saying is a vector field will emit a potential function if you can write it as a gradient of something. So let's do an example. Let's say that you would have, imagine that you take B to be x squared plus y plus xz. Okay, this is a scalar function, right? At each point in space, it gives you a number. So it's like a temperature function. Really, you think of this as a potential field, like electric potential or gravitational potential. Okay, and notice that the gradient of this function is 2x plus c, 1, and then x. So you would say that V is a potential for the vector field 2x plus c, 1x, because this vector field is precisely the gradient of this function. Now this is all a bit of cheating because I started with the vector, the function v, and then I took its gradient, and that's how I came up with this vector field. The point is that obviously the vector field, well, in a sense, it's like the important object. So like what you have to imagine is that I gave you some vector field, and I want to know if I can find a v with this property. Not what I just did, which is like, oh, just came up, I just invented my own favorite function and took its gradient. So really what we want to do in practice is reverse engineer this process where we start from the vector field and then find the potential. And I'll tell you in the next video how to do that. But for now, let's just see what are the advantages of having a vector field that emits a potential. And so the claim is that if F emits a potential, And notice that I'm saying a potential and not the potential, because we'll see that all potential functions differ by a constant. That's physically the analog of like the fact that it doesn't matter where you set up the initial height to be 0, like in these problems where you do things with conservation of energy. So the claim is that if F admits a scalar potential, then F is conservative. Okay. And so why is that? Well, what we want to see is that if you have started, the cool thing about this claim is that it would immediately give us a way to compute the work by just checking this. So let me try to explain this a little bit differently. So I'm saying, like, imagine that you chose a point P, a point Q. Choose your favorite trajectory. Let's say that you choose this trajectory, right, from time 1. So this one has position vector r of t. And you started at an initial time and a final time. Okay, and now we have a vector field F, right, which is here, and here, and here. But now, because we're assuming that it admits a scalar potential, this vector field is really the gradient of something. So it's always the gradient of some function. And so remember that the work in general would have depended on the trajectory, and still that's what we think it will happen. But you would always compute it as the integral from the initial time to the final time of the force field dotted with the velocity vector dt. Okay? But now, because this admits a potential function, right, you can change this F with the gradient So I'm replacing the force with the gradient because it admits a potential, right? Okay, and so what we're saying is that instead of doing this integral, it's the same as writing it in this way. But so now we're doing the gradient. We're doing the dot product of the gradient of a function with some velocity vector. And this should remind you very much of a formula that we saw before. So where did we see a formula that involved a gradient dot product a vector? Well, that was precisely the formula for the directional derivative. So this is precisely the directional derivative of the function v in the direction v, a little b. Here, I mean, I guess I'm already assuming implicitly that you were moving at unit speed, but that's okay, so that the velocity is a unit vector. If not, you have to rescale somewhere, but that's fine. You can always make that assumption. So really what we're integrating is a directional derivative. But this should be similar. Remember that the directional derivative is just a rate of change of your function as you move in a particular direction. This is like analogous to what happens when you do like an integral like this. Right, remember from Calc 1, when you do the integral of a derivative, this is just f of t2 minus f of t1. Well, really, there's a way to write directional. There's actually a way to write a directional derivative so that it actually looks like a derivative with respect to time, because this is just the rate of change in time as you vary, the rate of change of b as you move in with respect to time as you move in the direction determined by v, by the velocity. Really, the point is that the same principle applies, although we are using like a funny notation which does not look like a denominator, but essentially the same logic holds. And so what we find actually is that you have to evaluate the function, but now the function is a vector field, or sorry, is a scalar potential. So you have to evaluate the function, the potential at time t2. Okay, well, this is what we're calling tf, and then subtract the function at the initial time. Okay, and really this is being a bit sloppy. What I mean by this is that you're evaluating the potential at the position q, because that's what corresponds to the final time, minus the potential at the point p. So in other words, what I'm saying, and this is a key formula that we will use in the next video, so key fact, is that if f is the gradient of some potential function, then the work w, then w, the work from P to Q, right? From taking the particle from point P to point Q is, this is what we just found. But notice that this only depends, but the meaning of this is that the work is really just the difference in the change of potential, right? So it's a change in potential. So work equals, and this again may sound similar from your physics classes, so work equals change in potential function. So in particular, this only depends on Q and P, which are the final and initial endpoints. And notice that in this formula on the right hand side, the path disappeared. There's nothing in this formula that refers to the original trajectory that I chose. So notice that here, the trajectory chosen does not make a difference. Okay, so we have found the mine gold for generating a gold mine for generating conservative vector fields. You just find vector fields that are emit potential functions, and those will automatically be conservative. And then, as I'll tell you more about this later, but the main question is whether or not that's reversible, namely whether or not every vector field that's conservative emits a potential function, which is still not what we are saying. So next video, I'll do an example where we find the potential for a vector field and use it to compute the work.